this is example 5-1, flow through a nozzle. So we can see here we have a pipe that goes around a corner that has a nozzle on it. And we're given how much water is flowing through the pipe. That's the 0.002 meters per cubic second. Now we know what the diameter of the nozzle is, and we know what the diameter of the full pipe are. Now we are asked for the velocity and the pressure at point A, so that'll be right here. So I think we can start out by using the continuity equation just to find the velocity, right? If we know what the flow rate is and we know what the diameters of all these points are, then we can just use the continuity equation, right? So we can just say very simply, we know that total flow, that's what we're given, has to be the velocity at A times the area at A. That's just our definition of flow if we're using average velocities, which we're not given any more information, so we'll use average velocities here. So we can, of course, solve that for VA, right? That's just going to be Q over AA. Now, AA, it's a circular pipe, right? So it'd be pi over 4 times dA squared, or 4 times Q divided by pi times dA squared. Plug all those numbers in. See what we get. We get 4 times 0.002 meters cubed per second divided by pi, and then our diameter there is 30 millimeters, so that is 0.03 meters, and all that has to be squared. Put that in, we get 2.82942 meters per second. Let's see, we actually get meters per second. Yes, because we have cubic meters per second, we divide by meters squared. So that leaves us with 2.83 meters per second. All right, that's our first answer. Right, it was to get the velocity and the pressure. Now, what do we do for the pressure? Well, for the pressure, we can use Bernoulli's equation, right? Because we fulfill all the requirements, right? If we go from this point here to this point there, right? From point A to point B, we're in the center of the pipe, so it's always going to be the same streamline, right? So we can say we have an ideal fluid. Because it says water. Water flows through there, so it's incompressible and inviscid. We know that A and B are on the same streamline. And what else? We know it's steady flow. So based on all those, we know that we can use our standard Bernoulli's equation going from A to B. Okay, right. Let's write that out. So it'll be PA over gamma. It's all going to be water here, so I'm just going to leave the index off. Plus the velocity at A that we just calculated squared over 2 times G plus the elevation at A is equal to the same for B. PB over gamma plus VB squared over 2G plus ZB. All right, what else do we know right now? All we know is VA. That's because we're calculating it. Let's go back, and we're looking, of course, for PA. So we're missing ZA, PB, VB, and ZB. Well, let's start with PB. PB is right here, where the water comes out of the nozzle. That means the water is in contact with the atmosphere. So we can say at B in contact with atmosphere. That means we know that our PB is going to be atmospheric pressure. So in our case, if we're doing gauge pressure, it's going to be 0. So we know PB is equal to 0. All right. Then how about our ZA and ZB? Let's look up here. Well, we can say that the datum is on the center line of this pipe here, so both those are going to be 0. So we can say datum at center line of pipe. That means ZA is equal to ZB is equal to 0. That's nice, they drove off. So what are we missing then? We are looking for PA. We know VA, we know ZA, we know PB, we don't know VB. Okay. How do we get VB? Well, we get VB the same way that we got VA, right? So we can actually just steal from up here, right? Because again, the flow, the volumetric flow doesn't change. All that changes is the surface, or the area that it's going through, right? It's going from a 30 millimeter diameter to a 10 millimeter diameter. So we can say VB is 4 times Q divided by pi times now dB squared. Let's double check that we got that equation right. 4Q, yeah. So we got that correct. So we can plug those numbers in. 4 times 0.002 cubic meters per second. That of course doesn't change. Pi, and now my diameter was 10 millimeters, so 0.01 meters squared. And if we plug that in, we get, let me see here, 25.46479 meters per second. Although it's like a factor of 3 in diameter, like we get a much bigger change in overall velocity because of course we're looking at this, we have the squares in there, right? Okay, so now I think we have all that we need. The only unknown is PA, right? So we can rewrite our Bernoulli's equation. So we know that PA over gamma plus, let's put the VA in as a, oh, let's wait maybe until later, until we plug all those in, otherwise it might get too messy. So we have PA plus VA squared over 2G. The ZA was 0. The PB was 0. We know what VB is. And ZB was 0 as well. All right, so we can now go ahead and solve this for PA. All right, so we can say PA is gonna be, well, we have to subtract this and then divide by gamma. So we would have gamma over 2G of VB squared minus VA squared. Right, that's just writing it in a slightly nicer way. Now, what do we get for this? Of course, we can simplify with the G and the gamma here, because our gamma is just rho times G over 2G VB squared minus VA squared. So we would get, why did I write a sigma? Let's go back there real quick. Not sure, recently I've been writing sigmas instead of rhos. So it should be a rho times G over 2G VB squared minus VA squared. Of course, the G's cancel out, so we get rho over 2 times VB squared minus VA squared. All right, let's give us a little more space here. So that means PA is equal to, we have our rho over 2. And then now what do we get for, let's do square brackets. Our VB we have somewhere up here. That was, so that's going to be squared. So it'll be, we had that up here, right? That was 4Q divided by pi over dB squared. That's all squared. Minus our VA, which was the same. Of course, we could just take the numbers and plug them in, but let's try and do this as far along as we can with using variables. Squared. And now we can think about simplifying this a little bit. So this would then be still, we have the rho over 2. What else can we pull out? Well, we can pull out the 4 and the Q on top here. So we'd have 4 squared would be 16 times Q squared times rho. And on the bottom, we can pull out the pi. We have to be careful, it's pi squared now, which looks a little strange. 2 times pi squared. And then in our brackets, what do we have left? We have left, let's keep that as a square bracket. So we'd have left 1 over dB squared minus 1 over dA squared. So what can we do? I guess we can just square those out and then write them a little nicer. So that means here the 16 and the 2 create an 8. Q squared times rho over pi squared. And then in here, it would be 1 over dB to the 4th power minus 1 over dA to the 4th power, right? Because the square and the square. All right, I think that's about as simple as we can write this. So let's start with the numbers. 8 times 0.002 cubic meters per second. Let's not forget that we just square this. Times our density of water. We'll say at 1,000 kilograms per cubic meter. And we divide it by pi squared. And then back here we'd have 1 over, now dB was the smaller one, right? That was the 10 millimeter one. So it'd be 0.01 meters to the 4th power minus 1 over 0.03 meters to the 4th power. All right, and we can plug all that in. And then I get 320,225 pascals. So make sure that that actually works. We get we're dividing by meter to the 4th. We have 6, we have 3, so we have 1 meter left on top. And we need a kilogram meter per second, so yeah, we get newtons per square meters. So that then gives us 320 kilopascal. All right, so now we have the pressure at A and the velocity at A. Those are the two things. So 320 kilopascals in pressure and a velocity of 2.83 meters per second at this point in our pipe.